We're going to continue. In this case, we're going to solve section 6.6, which is solving exponential and logarithmic equations. What is the learning target is solve exponential and logarithmic equations and inequalities. Also, we are going to solve exponential equations, solve logarithmic equations, and I can solve exponential and logarithmic inequalities. As always, explore it. We can just work it in class. This is just an exploration of the topics that we are going to be covering today. So we are going to start with solving exponential equations. And exponential equations are equations in which variables expressions occur as exponents. You can use the following property to solve some exponential equations. So this is what we're going to do. We need to make sure, pretty much I'm going to say that the basis, this is b to the x equals to b to the y. The bases are going to be the same. Therefore, my equation is going to be x equals to y. And a brief example is 3 to the x equals to 3 to the 5. Then x is equals to 5. And we can see that one. Okay. So the property above is useful for solving an exponential equation when each side has the same base. That's important. We need to make sure the bases are the same. Okay, or we can rewrite those bases as the same. When it is not convenient to rewrite each side of an exponential equation using the same base, you can try to solve the equation by taking a logarithm of each side. So we are going to be taking a log on each side. Example number 1. So I'm going to have I have 100 to the x equals to 1 over 10 x minus 3. I'm going to take the first route. We're going to try to have the same base. I'm going to start with 100. I know 100 is 10 times 10, which is 10 to the second power. And I'm going to open a parenthesis to the x. Now this is equals to. I do have the 10, but it's in the denominator. So remember the property of exponents. So if I have 1 over a to the m, I can have it equals to a to the negative m. Okay, so a to the negative n, then we put it in the denominator. So we're doing the reverse process. So in this case, I'm going to have 10 to the negative 1 x minus 3. Now my bases are the same. I just need to get rid of this 2 and this negative 1. So I'm going to multiply power of a power. Okay, so I have 10 2x equals to 10. Let's be careful. This is negative 1 times x is negative x. Negative 1 times negative 3 is positive 3. Now, as we can see, the bases are the same. So my equation is 2x equals to negative x plus 3. And now we just solve the equation. In this case, I'm going to move my variable to the left. So I'm going to plus x. So I have 3x equals to 3. Then we're going to divide by 3. So x is equals to 1. Okay, this is the solution for my example A. We can try to verify that the answer is correct. In this case, we prove it already. Okay, so I'm not going to take much time. You can just give it a try in class to prove this one, to solve it. Now let's do B. B, in this case, I have 2 to the x equals to 7. This one is a little bit different because we don't have the same base. So what we're going to do is taking logs of each side. And I'm going to make sure that the log has the same base. the log have the same base. For example, I'm going to do log base 2 of 2 to the x equals to log base 2 of 7. Now remember the property that we have. If we have log base 2 of 2, that one was equals to 1, so we only had x. In this case, we're going to have that x is equals to log base 2 of 7. We don't have a calculator in this case that is going to calculate a base 2 to the 7 unless we craft that one in decimals or we use decimals. But in this case, we're going to use the change of base formula. So x is going to be equals to log of 7 over log base 10 of 2. And if we plug in that one in the calculator, we are going to get that x is approximately equals to 2.807. And this is going to be my solution to this problem. We're going to give it a try to the self-assessment later. We can try, let's give it a try this example number 2, okay? The self-assessment number 2. So what I have is 8 and I have 2. So I know that 8 is 2 to the third power. 2 times 2, 4 times 2 is 8. So I have 2 to the third power, okay? And I'm going to open parentheses, 2x minus 1 equals to 2 for x minus 4. I'm going to multiply 3 times 2 is 6, so I have 2. 6x, 3 times negative 1 minus 3 equals to 2 for x minus 4. My bases are the same, so I can just have 6x minus 3 equals to 4x minus 4. I'm going to do 6x minus 4 is 2x equals to plus 3 is still negative 1. So we divide by 2. So x is equals to negative 1/2. Negative 1/2 will be my solution. And in this case, we look at this negative 1/2. So negative 1/2 times 2, in this case, is 1 minus 1 is 0. And then if I plug in here, this one. So as we were saying, I have negative 1/2, right? So I have negative 1/2 times 2 is negative 1 minus 1. And we're going to put it together. Then I have 4 times negative 1/2 is negative 2 minus 4. So what I have here is 8 to the negative 2 equals to 2 to the negative 6. So which is equals to 1 over 8 to the second power equals to 1 over 2 to the 6th power. This is equals to 1 over 64 equals to 2 to the 6th power is 2 multiplied 6 times, which is 1 over 64, which checks the solution. So that solution is correct. And we're going to move to example number 2. Example number 2. Before we solve example number 2, we need to go over an important application of exponential equations is the Newton's law of cooling. This law states that for a cooling substance with initial temperature T sub O, the temperature T after T minutes can be modeled by T equals to T, initial temperature, minus T sub R, which is the surrounding temperature, e to the negative RT plus TR, okay? R is the cooling rate of the substance. So in this case, example number 2, you are cooking a licha, an utopian S2. This is an S2. When you take it off of the stove, if temperature is 212 degrees Fahrenheit, the room temperature is 70 degrees Fahrenheit, and the cooling rate of the stew is 0.046. How long will it take to cool the stew to a serving temperature of 100 degrees Fahrenheit? So I'm going to start writing the formula. So T is equals to T sub O minus T sub R e to the negative rt plus t sub r. I'm going to start replacing the variables. Remember that in this case, this is the cooling, this law states that for a cooling substance initial temperature, then we have to the temperature T after T minutes, and then we have the surrounding temperature. So in this case, the 100 degrees is the serving temperature. So I'm going to start with, this is T, equals to, the initial temperature is 212 minus the surrounding temperature, which is 70 degrees, e to the negative, the rate is 0.046, and then times t, that's what we are looking for, the time, and then plus 70. Okay, I'm going to subtract this 70. I'm going to move it to the left side. So 100 minus 70 is 30, equals to 212 minus 70 is 142, e to the negative 0.046 t. Okay, we're going to divide 30 divided by 142 is equals to 0.211, and this is an approximation, so this is approximately equals to e to the negative 0.046t. Okay, the bases are not the same, so what I'm going to do, because I have an exponential function, I have an e, I'm going to use the natural log, ln. Okay, so I have ln of 0.211 is approximately equals to, this one will take away the e, and what I have left is negative 0.046t, and this negative number is multiplying, so you're going to divide the left side. So I have ln of 0.211 over negative 0.046 approximately equals to t. I'm going to continue here. So t is approximately equals to 33 point, this case, if I use the calculator, 33.8. And this one is minutes. So what is my solution? This is an application problem. Therefore, you should wait about, this case I'm going to round to the nearest whole number, 34 minutes before serving the stew. Okay, that's example 2. We're moving to example number 3, but before we need to solve logarithmic equations. Self-assessment, we're going to work that one in class. Logarithmic equations. So pretty much the same situation. I need log base b of x equals to log base b of y. The basis needs to be the same in order to have x equals to y. Okay. The property above implies that if you are given an equation x equals to y, then you can exponentiate each side to obtain an equation of the form bx equals to by. We're going to see an example that explains that part. So in this case, I'm going to have example number 3. We're going to solve that one. Example number 3 says solve logarithmic equations. So A, I'm going to solve ln of 4x minus 7 equals to ln of x plus 5. Okay, so I do have natural logs on both sides of the equations, and this one is pretty much as the property that we have before, that log base b of x equals to log base b of y, so x equals to y. So remember that the natural log is the exponential. The natural log is the log of the exponential. function. So in this case, I'm going to have 4x minus 7 equals to x plus 5. And then we solve normal. I'm going to subtract x. So I have 3x is equals to plus 7 both sides. So I have 12. Then we divide by 3. So x is equals to 4. That's going to be my solution to this problem. Now let's do b. b in this case, I have log base 2 of 5x minus 17 equals to 3. Now, as you can see, the right side, I don't have any log base 2. So in this case, what I'm going to do is write a base 2 and then elevate it to the log base 2 of 5x minus 17 equals to 2 to the third power. Now I have the same base elevated to the log. So this one, remember, I'm going to say kind of cancels out. So I have 5x minus 17 equals to 2 to the third power is 8. And then we solve for x. So in this case, plus 17 plus 17, I have 25. So 5x equals to 25. And then we divide by 5. So x is equals to 5. And that's going to be my solution. Can we prove that this is correct? Yes. I'm going to do it here in this space. I'm going to use this red marker. So I have log base 2 of 5 times 5, because that's my solution, that's my x, my minus 17 equals to 3. And then we put a question mark. So I have log base 2 of 25 minus 17 equals to 3. 25 minus 17 is 8. So I have log base 2 of 8 equals to 3. Okay, so in this case, we pretty much know that this answer is correct because this is the base. 2 to the third power is equals to 8. And we're done. Or you can do, so look at this one. Log, I'm going to use this blue one. Log base 2 of 2 to the third power is equals to 3. So these 2 cancels. And what I have is 3 equals to 3. And the answer checks. Now, we are going to have one example where we're going to have what we call an extraneous solution. So that means one solution that does not work in our equation. So the example is you have log, and this is log base 10 of 2x plus log x minus 5 equals to 2. If I use the product property of logs, I can condense this beginning of the problem. So I have 2x plus log of x minus 5. So this one I can write it as log 2x times x minus 5 equals to 2. I can see that this is base 10. So I'm going to write 10 log of 2x x minus 5 equals to 10 to the second power. Okay, this log and 10 cancels out. I'm going to say cancels out. And I have 2x x minus 5 equals to 10 to the second power, which is 100. Apply this to the property. 2x times x is 2x squared minus 10x minus 100 equals to 0. I have a quadratic equation. I can divide by 2. All these terms are divisible by 2. So I'm going to have x squared minus 5x minus 50 equals to 0. And now I'm going to use the Xbox method. Remember, if I write an x, I'm going to have negative 50. And at the bottom, I'm going to have negative 5. I need two numbers that multiply each other will give me negative 50. If I add them or subtract them, will give you negative 5. Negative 10 and 5. Negative 10 times 5 is negative 50. Negative 10 plus 5 is negative 5. So in this case, I have x minus 10 and x plus 5 equals to 0. Zero product property, we're going to split, and I'm going to have x minus 10 equals to 0 or x plus 5 equals to 0. So I'm going to have that x is equals to 10 or x equals to negative 5. We need to test these two solutions because one is a extraneous solution. I'm going to say, to save time in this long video, that the first solution is correct. Okay, so in this case, if you plug in 2 times 10 is 20, okay, and then I have 10 minus 5 is 5, and if we condense, we're going to get equals to 2, okay? But with negative 5, I'm going to focus on negative 5. So I have log base 10 of 2 times negative 5, and I'm going to stop here because this one is log of negative 20. And remember that we cannot have negative numbers. We cannot calculate the logs of negative numbers. So x minus 5 is my extraneous solution to this problem. But x equals to 10, let's try this one here. So for example, I have log base 10 of 2 times 10, right? Plus log of 10 minus 5 equals to 2. So I have log base 10 of 20 plus log base 10 of 10 minus 5 is 5 equals to 2. This is an addition, so the properties of logs multiply those two numbers. So 5 times 20 is 100, so log base 10 of 100 is equals to 2. See, 100 is 10 to the second power. So log 10 to the second power is equals to 2. These two cancels out, so I have that 2 is equals to 2. So the first answer checks. I just changed my mind about proving that number. We're going to solve some of these problems in class. So if you have any question, let me know if you want me to solve any of those problems and put it on a video. So the last part of the notes, we are going to have solving exponential equations and solving exponential and logarithmic inequalities. And we need to be careful with this one because remember that we have a range to work with. So number one, an exponential property of inequality is pretty much the same as the equations, but we need to be careful with the inequality symbol. Okay, with inequality symbol, because remember that the logs we cannot have negative numbers in the logs, so we need to be careful with those ones. That's exponential and this is logarithmic, and we're going to solve the first example. So for example, I have 3 to the x is less than 20. What can I do? In this case, I'm going to, because I cannot transform 20 as a base 3, so what I'm going to do is log base 3 of 3x is less than log base 3 of 20. Okay, so what I'm going to have is x is less than log base 3 of 20. I cannot use, in this case, a calculator, so I'm going to do a change of base, and in this case, x is less than log of 20 over log of 3. And what we are going to have is, if I plug in everything, is x is less than 2.727. That's going to be the solution to the problem. Okay, you can use decimals or you can use a calculator, and we're going to get that solution. And let's do, in this case, the log. So it's the log. Remember, we need to be careful with the logs. So I have log base 10 of x less than or equals to 2. So in this case, because it's base 10, I'm going to have 10 log of x is less than or equals to 10 to the second power. So what I have is x is less than or equals to 10 to the second power is 100. Now, here's the part. Because I have a log, I need to be careful with the negatives. So my solution, I'm going to write it here. I'm going to write it here as a reminder, because log of x is only defined when x is greater than 0, then the solution is, now here comes the solution. The 100 is correct, so we have 0 is less than x less than or equals to 100. So it's all the numbers, including 100, that are less than 100. 99, yeah, I was going to speak Spanish. 99, 98, 97, 95, 80, 67, 50, 20, 10, 1, but not 0. 0 is not going to be included in that solution, and neither the negative numbers. So that's going to be my solution. And again, we're going to solve these ones in class, or if you want to give it a try here, just let me know and I will do it. If you have any question, let me know. And thank you, and I'll see you later.